So the pigeonhole principle can be used for all sorts of different things, particular discrete objects like we've talked about previously. We've seen examples that use large populations or large groups, and just applying the pigeonhole principle is sufficient. I want to show you an example that's a little bit more classical, as in the sense that a lot of the earlier examples of using the pigeonhole principle were associated with number theory. So I'm going to give you an example that's a number-theoretic example. Now, to do this, I'm going to give you a little bit of number theory that we are going to use to prove a claim for which the pigeonhole principle is going to be very helpful for us. So an integer n is divisible by d if there exists, if there exists some integer k such that n is equal to k times d. So you could think of k as that multiple such that you multiply it by d to get n. So this is some pretty basic stuff, at least I think it should be. Now I'm going to present you a theorem that's going to take advantage of what we know about divisibility. So I'm not going to prove this theorem for you, but it's a very helpful number-theoretic theorem. So it's very often called the Quotient-Remainder Theorem. I'll abbreviate the QR part. Quotient remainder is QR. And it's stated as follows. So given any integer n, and positive integer d, there exists unique Q and R. So these are unique. So these are determined by n and d. These are unique Q and R that are going to be integers, so that n is equal to d times q plus r, and it has to be that the r value, so what r is between 0 and d minus 1. So it has to be less than d. So keep in mind that we're putting this in the context of us talking about divisibility. So we're talking about if I give you n and I give you a number I want to, like, say, for example, to divide by d, for example. So the idea is that I have two unique, so determined from n and d, two unique q and r, so that you could rewrite n like this. So n is going to be some multiple of d plus something called r. Now r, I gave it that name explicitly for us here because this is the remainder. So that's the part that's going to be important for us for today. So we call that the remainder. So you might know that phrase from somewhere when we talk about division. Now, if you, for example, say, for example, you learned long division, you may have learned something called the remainder. So when you carry out long division, you end up with something at the end called its remainder. It ends up being an integer. So that's what R is. We're going to see how we're going to use this QR theorem to help us, the Quotient-Remainder Theorem. So here's the claim. So here's a theorem. We're going to let n be a positive integer. For any set of integers, I'm going to call it set A. It's going to have A0, A1, A2, all the way up to AN. It's going to have n+1 integers in it. With n+1 integers, my eye's sort of melting there. Not this eye, that eye. There exists two integers, AI, AJ, which are going to be in A with I not equal to j. This is just to guarantee that they're not the same element, such that ai minus aj is divisible by n. So when you see this, you're looking at this like, well, I see some things that remind me of the pigeonhole principle. You see something that's slightly, like it looks like n+1, which is like one higher than a something, right? So that's like the first thing that might glare at you when you see a statement like this. However, other than that, it doesn't look really clear at all what exactly we would need to do if we wanted to use the pigeonhole principle. And I must stress that this is just one example. The pigeonhole principle may not apply at all to your given problem. This is just an example showing you kind of the mindset, the mentality you might go about when we're thinking about kind of number-theoretic claims, asking questions about divisibility, for example. So here's the game plan. And it comes down to how the QR theorem, the quotient-remainder theorem, works. So what did the quotient-remainder theorems tell you? It told you that if I give you any two numbers, in particular an integer n and a positive integer d, what it did was it told you that there's only certain numbers of remainders possible, right? So what did the QR theorem say? So the game plan I have in mind is that the remainder is going to be something between this, right? It's going to look like this, right? But those are all integers, right? Those are all integers. But what does that actually look like? And remember, d here is that's the number we're talking about for divisibility, like the closest multiple. And at least that's the intuition that we had. Over there, it's n, right? So, but just to keep it simple, I'll just keep d over here. That means that the remainders can only have these values. How many are here? Well, that's d many. There's d many possible remainders. And that's the other ingredient that we're going to need here. Does that give you any ideas what we might try to do here? So remember, any integer, when I use the QR theorem, it says I could rewrite it by some multiples q of whatever I'm dividing by, plus a remainder. And the theorem says that the remainder is somewhere between these two values. That means that it has this many possible values, because it's an integer. So let's use this now. So let's take these two ideas together. We're going to try proving the claim. Observe that any integer divided by n by the QR theorem has remainder r that satisfies 0 is less than or equal to r is strictly less than n, because that's what d is. So we're going to comma, let's put a comma there. We're going to let this be a set. We're going to call it r. So this is just going to be a capital R here. It's going to be the numbers 0 all the way up to n-1, akin to what I wrote over here. So that's a finite set, right? So each integer of A And remember, the statement is about any set of n+1 integers. These could be negative. They could be anything that is an integer. There's nothing saying that, oh, this number has to be less than that number. No, these are an arbitrary set of integers. That's the wild part about this. So just watch. So each integer of a, when divided by n, has some remainder in R. This should remind you a little bit of what we talked about for tips for applying the pigeonhole principle. So far we have A, we have R, and we also have this thing saying that every one of the integers, when I divide them by n, has some remainder. So every integer has some remainder, right? That's because that's from the Quotient-Remainder Theorem. So that tells us something. Well, how many integers are there? There's n+1 integers. How many integers are in this set over here? There's n of them. There's one more than the number in this set. So we could use the pigeonhole principle. There are n+1 integers. There are n+1 integers in A, or elements, and n integers in R. So, by the pigeonhole principle, at least two integers, that integer is sort of looking like it kind of stayed outside a little too long out in the cold weather. AI, AJ in A with I not equal to J, because they're two different elements, right? Have the same remainder. So there's going to be two of the elements in A that have the same remainder when divided by n. Now let's bring this all together. So now we know that there's at least two integers in the set A that have the exact same remainder. So now we're going to use this information carefully. Now, the Quotient theorem was helpful for us for this detail, right? We're going to use it again to now write those two integers. So now we got these two integers here, I and AJ. I would like to know what's going on with those two. So let's take a look at what's going on with those two. So we're going to use the Quotient theorem again. So applying the Quotient theorem. Now we're going to just rewrite what those two integers that we derived, or what we obtained. We're going to take those two integers we obtained. We're going to apply the Quotient theorem to each one. There exists. Why? Because the Quotient theorem says that there's that integer q, and then there is the integer that's the remainder, right? They're unique. They get determined by in this case, this would be that integer in the set A versus n, which would be the positive integer here. There exists q1 and q2. So I'm going to have two of them because I'm going to use the definition twice technically. So these are my multiplicative numbers, or multiples, and integers. We're going to have R1 and R2. They're going to be the R2 remainders. They're going to be between 0 and n. Well, 0, but includes 0, just to be clear. so that AI is going to be equal to Q1 n plus R1, right? That's what the theorem says that we could do, right? Is we could write it by some multiplicative closest multiple plus the remaining bit that gets me to AI. And we can do the same thing here. AJ is Q2 times n plus R2. And now I'm just going to take the difference between AI and AJ, right? Because that's really what we're curious about. Because I know they exist. I don't know which one it is in A, those two. I don't know which ones they are. But I know they exist. Like I said, it doesn't have to be constructive. And by taking their difference, I'm going to take AI and subtract AJ. And watch this. You're going to see a definition pop up that'll remind you of something. So let's watch this. So watch this carefully. I'm just going to write what each of these equations tells me AI and AJ are. Q1 times n plus R1 plus Q2 times n plus R2. Well, these both have, like I could just drop these parentheses and notice I have Q1 and Q2 that they're both related by n. So I'm going to factor there. I'm just going to regroup the remainders together. And then you end up with the following. This is equal to Q1 minus Q2 times n plus R1 minus R2. But what did we say about R1 and R2? What did we say about those two? What did we say about those? What did the pigeonhole principle? Why did we use the pigeonhole principle? We showed that these two have the same remainder, right? That's why we picked AY and AJ the way we did. So these two are actually equal to each other. R1 is equal to R2. That's because we used the pigeonhole principle to say that there's at least two integers. It's these two right here, right? That have the same remainder. But that means that this right here, what is this equal? That's 0, right? Because it's the same number. So it means that this is actually equal to just Q1 minus Q2 times n. Are we done yet? There's something that we're not technically done yet, but there's something very important I want you to observe about this. What did we say for an integer? So if I give you an integer, now keep in mind that AI minus AJ is equal to this. So what did it mean for me to say that AI minus AJ is divisible by n? What would that mean? Remember, we said that there exists an integer such that that integer times n would be equal to my number. Is Q1 minus Q2 an integer? Yeah, because it's an integer subtract another integer, so the result of that is an integer. So this is, that's it. This is an integer, right? Therefore, since Q1 minus Q2 times n is divisible by n, AI minus AJ is also divisible by n. And that completes the proof. Piece of cake, right? So notice the strategy. All we did was now you might say, Dan, how did we know to use the pigeonhole principle here? Well, normally when you play with a statement like this, you have to be careful, and it's about identifying key aspects of the statement. Because proving things ain't easy all the time, believe me. You can spend months, even years, focusing on one statement and seeing if it's true or not. But this one is really nice because we identified those key couple observations, namely the number of elements that were in the set A, right? The next thing we also observed was about the Quotient-Remainder Theorem told us about the number of remainders that were possible. And then we tried to associate each integer in A with one of its remainders. Well, each one has exactly one, right? Because it's unique. So remember, that's a part of the Quotient-Remainder Theorem. So that means that when we talk about that, each integer in here has a remainder. And there's one less remainder than possible at most compared to the number of elements, because there's one more. So keep in mind, you could not use the pigeonhole principle if there's one less element in this set. That's really one thing I really want to point out to you, is that because otherwise we couldn't use it because it doesn't meet the conditions of the pigeonhole principle. But once we did that, we were able to identify A on AJ as per the statement, because it was a statement about the existence of two integers that were unique. That's another telltale sign you might be looking at something like this. It may or may not be the case, but it's a nice idea maybe to start off. Something to think about. And then once we did that, we used it again, and we simplified. And then we just looked at what the definition means for something to be divisible. Piece of cake, right?